Hi everyone. Today we are happy to have Scott, who is going to talk about complex Liouville.
Okay, well, thanks very much for the invitation. I'm really happy to be here and always love coming to Chicago. Good to see everyone. So today I'll tell you about the series of projects that appeared over the past few months, together with my amazing collaborators, Lawrence Eberhardt, Beatrix Muhlmann, and so let's get right into it because we're already starting a little bit late. So this is a talk about two-dimensional string theory. And I really like these low-dimensional string theories because I think of them as providing sort of controllable theoretical laboratories in which you can really investigate fundamental questions of quantum gravity. They're simplified settings, but oftentimes they retain the essential physical characteristics that you want to understand. And what I really like about them is that they provide an environment that I think is somewhat rare in the sense that you can derive and sometimes even prove new holographic dualities in this paradigm. Now, over the past few years, of course, there's been a lot of interest and activity around a particular model of two-dimensional dilaton quantum gravity known as Jakiv-Teitelbaum gravity, which was recently embedded in a paradigm of dualities between two-dimensional theories of quantum gravity and matrix models. And one of the outcomes of this recent flurry of activity is that JT gravity has been embedded in string theory, where it's been realized by a semi-classical limit of the well-known 2, p minimal string and of the recently discussed Virasoro minimal string that I actually talked about here last year. Now, this is all great. This flurry of activity has been very productive, but in parallel, I think it's fair to say that there's a stark dearth of precise models of de Sitter quantum gravity, describing universes that more closely approximate our own, even in low dimensions. Now, there has been some activity on low-dimensional de Sitter quantum gravity, but I think it's fair to say that no new unifying picture or conceptual framework has emerged despite this activity. Nevertheless, I want to advocate for the viewpoint that low-dimensional models provide a controllable setup in which we can formulate and ideally even solve microscopic models of quantum. Okay, so the paradigm that's emerged in these models of two-dimensional string theory is the following. They involve paradigms between two-dimensional string theories with some specific worldsheet CFT. On the one hand, these worldsheet CFTs involve some matter CFT with some central charge coupled to Liouville CFT with central charge 26 minus that of the matter theory. And together with the BC ghost, this forms a critical worldsheet theory. And in this paradigm, this class of families are dual to double-scaled matrix integrals. So this is a theory of some n by n Hermitian matrix M, integrated and weighted by some potential B. And in particular, these dualities involve matrix models in the so-called double scaling limit, where you take n to infinity and zoom in on some region of the eigenvalue spectrum. So I think of these theories as occupying some landscape of two-dimensional solvable dualities, and we can parameterize this landscape by the complex plane of the central charge of the matter theory. And there have been some notable entries in this landscape, and I'll discuss them in turn. But the sort of big question in the back of my mind is, to what extent can we classify and solve this landscape? So the first is a familiar one. It involves the 2, p minimal string, which on the worldsheet involves coupling a 2, p Virasoro minimal model together with Liouville CFT. And these occupy a discrete set of points in the negative central charge axis. And it's been understood for quite some time that this class of models is dual to a double-scaled one matrix integral, meaning there's just one matrix in the sense of this kind of model, with a leading density of eigenvalues given by this cinch formula. And by a topological recursion of the matrix model, this completely solves the theory, at least at the level of strict perturbation theory. And indeed, it's been recently understood that in some sense, in a semi-classical limit where you take this p to infinity so that the central charge goes off to minus infinity, this density of states becomes the famous cinch square root E density of JT gravity, and in some sense, this semi-classical limit describes JT gravity. Moving on up in complexity, we have the more general P comma Q minimal string, which just involves some more general P comma Q Virasoro minimal model on the world sheet. Now, again, it's been for quite some time been understood that this class of models is dual, not to a single matrix model, but to a two matrix model, meaning there are two fundamental matrices in this kind of description, coupled in some minimal way. And this class of matrices is fully characterized by a Riemann surface known as the spectral curve that characterizes the density of eigenvalue, or the eigenvalue distribution rather. So in particular here, you have the Ising model as one of the entries in this landscape. This carves out some dense but rational set of points on this C less than 1 region. Now, last year, I told you about the Virasoro minimal string, or at least those that were here last year. And this involves a slightly different worldsheet theory where we couple Liouville CFT with general central charge, say bigger than 25, to a sort of cousin theory that is known as time-like Liouville theory, which has central charge less than 1. And if you combine these theories, this constitutes a critical worldsheet system. And by some detour through an elegant relation with 3D gravity or Virasoro TQFT on the worldsheet surface times a circle, we were able to understand that this model is precisely dual to a double-scaled matrix integral whose leading density of states is given by what is, in a precise sense, the Cardy formula for the asymptotic density of states in 2D CFT, where here E is the eigenvalue of the matrix. Now the observables in this theory, the string scattering amplitudes, turn out to be just polynomials in the momenta that characterize the external operator insertions. This is some miracle if you think about it from the point of view of string perturbation theory. And in a precise sense, these string amplitudes, we call them quantum volumes, could be thought of as a sort of quantum deformation of the Weil-Petersen volume of the moduli space of the surface sigma, on which you're studying the worldsheet theory. And in the B to 0 limit, in which the central charge of this Liouville theory goes to infinity, note that here I'm viewing the Liouville theory rather than the time-like Liouville theory as the matter theory, but that's just so that I can present it on this other region. Anyway, in the limit where the central charge of the Liouville theory goes to infinity, this theory reduces to JT gravity, and indeed this density of eigenvalues reduces to the JT version or value. Okay, so today, finally, I'm going to tell you about a new entry in this two-dimensional landscape. It lives on this vertical line in the complex C plane, and it involves coupling two copies of Liouville CFT, but with complex central charge, such that the central charges add up to 26. And I want to emphasize that this is not simply the analytic continuation of this away from this C bigger than 25 region, for the simple reason that time-like Liouville theory is not the analytic continuation of ordinary Liouville theory. And I'll tell you that this model is precisely dual to a double-scaled two-matrix integral like that of the P comma Q minimal string, characterized by this spectral curve involving these cosines. Now, the observables of the theory, like in the Virasoro minimal string, are of course just string amplitudes, integrated correlation functions of the worldsheet CFT over the moduli space. And these turn out to be a significant step up in complexity from the quantum volumes of the Virasoro minimal string. So they're no longer simply polynomials in the external operator momenta. They'll exhibit some rich analytic structure, in fact, that I'll get to in a few slides. But nevertheless, they will be computed exactly, at least in string perturbation theory, by topological recursion of this dual matrix model. So here's the outline for the rest of the talk. I'll tell you about the worldsheet description of this theory involving coupling two copies of Liouville CFT. I'll then move on to discuss the dual matrix model and how topological recursion exactly solves for the string amplitudes of this theory. And in the second half of the talk, I'll tell you about what, to me anyway, is the most exciting aspect of this theory, which is that it appears to capture some aspects of pure three-dimensional de Sitter quantum gravity, and thereby provides an entryway into the holographic formulation of quantum cosmology in low dimensions. Okay, so I'll begin by getting into the worldsheet theory. Before moving on, are there any questions? Yep.
So is there a way to take general real parts and general imaginary parts, or
What do you mean?
Like the two Louisville CFTs,
Mhm.
you only have like a constraint on like the sum of their central charges, right?
Yeah, that's right,
So-
that's right.
Could you imagine like instead of just picking 13 to be a different number and then adjusting the other guys?
Yeah, and in fact, there is some sense in which you can continue the observables of this theory to like the rest of this complex C plane. But there will be some caveats to that, but in general, it's straightforward to continue the observables, just because Liouville theory is well defined away from that regime, but some conceptual aspects of the story will be different, and I'll try to highlight those.
I guess another way of asking this question is, does de Sitter gravity pick out this factorization into?
Yeah, de Sitter gravity does pick out the
Okay,
factorization
thank
to 13 plus or minus I number.
This spectral curve, do I allow myself arbitrary Z? Is it a whole bunch of, like a whole chain of things for? What does the spectral curve look like if I just actually graph it?
We'll get to that. Yeah, there'll be multiple branch points, infinitely many branch points in the complex Z plane. There'll be infinitely many nodal singularities. It's like you took some infinite genus surface and collapsed it upon or down on all the cycles. We'll get to it in a bit. Okay, so the worldsheet CFT, I've basically already told you the setup, but let's spend a bit more time on the details. So it involves coupling these two Liouville CFTs with complex conjugate values of the central charge. I'm a bootstrapper, so I think of the worldsheet theory as being defined by the non-perturbative CFT data associated with each of these worldsheet theories. So we'll parameterize the central charge in terms of this common, this B variable that often shows up in Liouville theory. In the case of interest, this will correspond to B squared being purely imaginary. So B has a funny 45-degree phase. The spectrum, so the observables that you can consider in this theory are fixed by the spectrum of local operators. And this is a continuum of scalar primary operators whose conformal weights are given by, in terms of this P parameter, or Liouville momenta parameter P in this way. And finally, to compute observables in the theory, you need to know about the structure constants of these spectrum of primaries. And these were famously bootstrapped by Dorn, Otto, and the Zamolodchikovs, culminating in this famous DOZZ formula. Now, the absence of the Weil anomaly of the worldsheet theory means that the central charges add up to 26. And as I said earlier, that corresponds to the case that B has this funny pi/4 phase. Now, the mass shell condition also implies that the conformal weights have to add up to 1. And what that means is that these P parameters have, it's convenient to give them the opposite 45-degree phase. Now, together with primaries of the two component worldsheet theories, we combine the two primaries from each of the theory, make sure the central charges add up to 26 and the conformal weights add up to 1. And these are the on-shell vertex operators that we'll study in the rest of the talk. Now this Liouville theory is completely solved in terms of this DOZZ formula, so you can compute any worldsheet, any local observable you wish, simply by using the conformal block decomposition on the worldsheet. And here I wrote down the specific value of this DOZZ formula just to convince you that it exists. It involves these funny Barnes double gamma functions, but you don't need to know anything about those for the rest of this talk.
So is this some new solution to the recursion relations that gave rise to the DOZZ?
No, this is still ordinary DOZZ, just analytically continued away to complex central charge. Unlike time-like Liouville theory, which is a different solution. Yeah, that's right. The point is that the structure constants that compute that you can use to compute the local observables are explicit meromorphic functions, and in principle, you can put it on a computer. Integrate conformal blocks weighted by these structure constants. And the main point is that this gives us a significant amount of analytical leverage over the worldsheet theory, and we'll uncover some important aspects of the theory. Okay, so let's get right into it. The simplest observable in the theory is, of course, just the sphere 3-point amplitude. And it's the simplest observable in the theory because there's no moduli space to integrate over. So you just combine the 3-point functions in the two theories, and that defines this sphere 3-point amplitude. And the result actually, as has been known due to work of Zamolodchikov since 2005, is an explicit elliptic function of the three momenta that can be determined entirely just by knowledge of the poles and zeros of the DOZZ formula. And this sort of strategy where you use the analytic structure of the worldsheet correlation function to leverage that into some knowledge of the analytic structure of the string amplitude will be a theme in what follows. So anyway, this sphere 3-point amplitude, which with a convenient normalization of the external operators, is given by this explicit elliptic function. Notice there are these Jacobi theta functions, theta 1 and theta 3 here. Now, we found it convenient to rewrite this as an infinite sum over this integer m, where the summand takes this simple factorized sine form. And it will become clear in what follows why we like this rewriting. Okay, so in more general string amplitudes, we have to integrate correlation functions of the worldsheet CFT over the moduli space of the Riemann surface. Now remember, we focus on the case where the central charges are complex conjugates and the conformal weights add up to 1. And I just want to highlight in advance that this implies that the conformal weights live in the principal series of SL2C. So in this case, the worldsheet moduli integrand assembles into an absolute value squared. And moreover, for these choices, this worldsheet moduli integrand is in fact an absolutely convergent integral over the moduli space of Riemann surfaces, which is not typically the situation in worldsheet string theory. And finally, it will be convenient to consider the analytic continuation of this observable in P away from this 45-degree ray. And that will be essential in revealing the analytic structure of this string amplitude, which will provide some essential clues about their closed form.
So there are no divergences and boundaries of moduli space?
No, at least when they live in this domain. You can continue them away from this domain, and then you'll start running into divergences, which will give you some leverage on the analytic form of the amplitude. For example, if you continue these P's, you'll discover some infinite set of poles and eventually discontinuities that come from this moduli integral starting to diverge. Okay, so the point is that this explicit computation where you integrate these correlation functions over the moduli space is extraordinarily complicated. Even the correlation functions themselves involve integrating Virasoro conformal blocks, which themselves do not have a closed form, weighted by these DOZZ formulas, which involve these funny special functions. So this is a tremendously complicated thing. So our strategy, instead of direct computation, will be to harness this analytic structure together with symmetries of the worldsheet theory in order to initiate a sort of bootstrap for the amplitude. And what we'll find is an infinite set of poles, which come from resonances of these Liouville CFT correlators themselves, when they reduce to some Coulomb gas integral. And there will also be discontinuities associated when this moduli integral starts to no longer converge because you've continued the momenta away from this convergent regime. Other ingredients are symmetries of the worldsheet theory. There's one that we call a duality symmetry that involves inverting B. Now this is just a tautological symmetry of the worldsheet theory. The central charge is invariant under doing this. There's also a swap symmetry where you complex conjugate both B and P, and this just has the effect of swapping the two worldsheet theories, which are themselves complex conjugates.
So that's supposed to say IB goes to minus IB at the bottom?
No, because B has this funny phase. I should have just put B goes to B star. But because B has this pi over 4 phase, multiplying by I is complex conjugation.
That's a unitary operator in the Hilbert space that does that?
Well, I'm not sure which Hilbert space you're talking about because it changes the central charge of the.
So what sense is it a symmetry?
The symmetry of this amplitude, because it just has the effect of exchanging the roles of the two worldsheet correlators. Like, right, this amplitude will be some function of B and P1 through Pn. And because of its definition, this function has to be invariant under these operations, which are just sort of tautologies from the worldsheet formulation. But they're non-trivial constraints viewed as like constraints on this as a function of B and P's. The idea is that we use these poles and discontinuities to bootstrap the amplitude. If you have some ansatz, the result of that, the combination of things that contribute these poles and discontinuities has to assemble into something invariant under these symmetries. Okay, so just to make the point how powerful these constraints are, if you combine these constraints, so the analytic structure of the worldsheet, moduli space integral together with these symmetries of the worldsheet theory, you get a solution for the sphere 4-point amplitude, which is unique if you make some mild assumption on the growth of this amplitude at large values of P. And there are sort of two qualitatively different terms that I want to highlight here. The second one involves a sum over two integers, m1 and m2. Remember the infinite sum form of the 3-point function that I wrote down earlier. But there's also a sum that just involves a single integer m, where the m value, it's the argument of the sign here, takes the same value, weighted by this observable V04, which is this specific quadratic polynomial in the four momenta. And in fact, this observable is nothing but the analytic continuation of the string amplitude of the Virasoro minimal string that I discussed earlier. So it's quite striking that somehow this Virasoro minimal string amplitude that we call the quantum volume plays some role as a sort of building block of this complex Liouville string amplitude. So this is just to illustrate the power of this bootstrap philosophy. And just to put any doubt to rest, we put it on a computer and carried out the numerical integration. And this is straightforward to do precisely because the moduli space integral just converges. So here's an example where we have the central charge live in this 13 plus I whatever regime and pick three values of the external momenta, fix three values of the external momenta with this minus pi over 4 phase, and then dial the magnitude of the fourth momentum. And what we find is a result that agrees with this sum up to some very small degree of error. Moreover, we can do what I mentioned earlier and analytically continue the central charge away from this 13 plus I region and even give somewhat random phases to the momenta, and we still find an answer that agrees with the analytic continuation of this ansatz. So this is why we have some confidence that it's straightforward to continue the worldsheet theory away from this special locus. Okay, so that's it about the worldsheet theory. Before I move on to the matrix integral, maybe I should pause for questions. Okay, so let's start with a bit of a crash course on two matrix integrals. As I mentioned at the beginning of the talk, they may be familiar to you in the physics literature as the duals of the P comma Q minimal string, just for example. They're similar to the one matrix models that arose earlier, but now they involve integrals over two fundamental matrices, M1 and M2. So M1 and M2 are each n by n Hermitian matrices, but now the path integral is weighted not just by potentials for the two matrices individually, but by some minimal coupling. Now, in the matrix model literature, the main or primary observables of these kinds of models are known as resolvents, and resolvents in particular with respect to one of the two matrices, because now remember there are two matrices. But let's pick, say, the first matrix. This involves a trace of 1 over x minus m. And this observable at finite n exhibits a pole whenever x coincides with an eigenvalue of m. Now we're interested in this double scaling limit where we take n to infinity and zoom in on some region of the eigenvalue distribution. And in this limit, these resolvents admit a topological genus expansion. So here, e to the minus s naught is some parameter that we keep fixed in this double scaling limit. That's some avatar of n. And the observables admit this topological genus expansion with these perturbative resolvents, Rgn being the perturbative observables of the theory. However, in this double scaling limit, these resolvents no longer just exhibit poles, they are now multi-valued functions with branch cuts that live on the eigenvalue distribution. So the spectral curve that I mentioned earlier, we should think of it as defining a Riemann surface on which this resolvent is single valued. It's a multi-sheeted cover of the complex plane. Okay, so my claim is that the dual of the complex Liouville string is characterized by this spectral curve, the specific spectral curve involving these cosine formulas. It looks pretty innocuous and harmless on its own, but it has some features that may be unfamiliar if you played around, for example, with the p comma q string at all. For one thing, and I mentioned this earlier in answering a question, it exhibits infinitely many branch points. So these are points where either dx or dy vanishes, and they're labeled by this integer m. A priori, m could be any non-zero integer. I say I'm excluding 0 here because both dx and dy vanish at that point. Now it also exhibits infinitely many nodal singularities. These are points at which the spectral curve pinches itself. And these are characterized by a pair of integers, r and s, which we can take to be positive integers. And for the experts in the older literature, this is actually remarkably similar to the spectral curve of the older p comma q minimal string, but in a parameterization where root z is something like the fzzt parameter. That was a comment strictly for the experts. And I want to highlight, again, this integer m, which labels these infinitely many branch points, because that will be an important structure in what follows. Okay, so for example, one thing you can extract from this spectral curve is the leading density of eigenvalues of one of the two matrices, having integrated out the other. So for example, let's look at the leading density of eigenvalues associated with the first matrix. We call this rho 0 superscript 1 e. Now there's some prefactor. Remember here that b squared is pure imaginary, so these combinations are real and in fact positive. And the density of states involves this sign of arc-cosh e over 2 structure. And if you look at it, it exhibits the familiar square root edge of double-scaled matrix models near the edge of the eigenvalue distribution, which I took to be 2 here. It goes up for a while, and then it eventually comes down and hits 0. So there's some energy that we call E naught, where this density of states hits 0. And that seems bad if you want to interpret this as a density of eigenvalues. So you might worry that this spells doom on the theory, but never fear. I actually won't talk about it in the rest of the talk, but this is, in a precise sense, a non-perturbative effect. And this is precisely the point at which the contour of integration over eigenvalues has to be deformed into the complex plane due to the presence of some worldsheet instanton effects. So if you're interested in that, please ask me after the talk. But don't worry, all this is to say that I think this matrix model based on this spectral curve is still well defined, despite this funny feature of the density of eigenvalues.
But if you integrate over the place where, if you integrate over that blue curve, do you get n?
We'll get to what integrating over this region where the density of eigenvalues is positive defines. It doesn't. If you're talking about n of the matrix model, no, because that's infinity. It is a double scaled model. It is proportional to e to the s naught, which is some residual notion of the number of degrees of freedom. But yeah, we'll get to it in a little bit. Okay, so in these double scaled matrix models, the spectral curve entirely determines these perturbative contributions to the resolvents that I wrote up here. And so in that sense, it solves the theory, at least in the genus expansion. So the spectral curve defines these inputs to topological recursion, omega 0,1 and omega 0,2, and together with that input, you can compute any of these perturbative contributions to the resolvents. And one novel feature of the topological recursion of this model compared to say that of the matrix model dual of JT gravity or of the Virasoro minimal string is that it involves this infinite structure, this additional structure, which involves a sum over these infinitely many branch points of the spectral curve. And the dictionary between the string amplitudes and these resolvent differentials is a simple integral transform. something like an inverse Laplace transform, which when you process it involves some infinite sum over residues at these branch points of the spectral curve with this simple integral kernel. Okay, so that I claim is the dictionary between the string amplitudes in the worldsheet theory and the resolvent differentials of the double-scaled matrix model.
Does this converge in the coupling or
In which coupling?
in the G?
The sum, you mean if I take the string amplitudes and sum over G, is that convergent? Is that what you're asking?
Yeah, just the right hand side.
The right-hand side is very well convergent,
Ah.
yes. If you wanted to sum it over genera, then you would start running into problems, which is related to this, these instanton effects.
Like, does it have like some factorial growth?
Yeah, there's some 2G factorial growth asymptotically.
So in the previous plot of, what happened, where do I see all of this complicated structure of?
You don't, because we're looking at a simple observable here, just the leading density of eigenvalues. Yeah, you don't see this additional structure, but the more complicated resolvents exhibit that structure. There'll be some sum over, well, I mean, okay, you can't see it here, but if I was to write down formulas for omega 04, it would exhibit the more complicated structure. Qualitatively similar anyway to those of the amplitudes I wrote down. Okay, so just to make the point that the topological recursion of the matrix model solves the worldsheet theory and string perturbation theory, it actually leads to a general expression for these string amplitudes over a sort of Feynman diagram for the closed string theory. And the technical word for these Feynman diagrams are colored stable graphs. So I'll go through this. This is, I think, easily the most technical slide of the talk, so I'll try to go through it slowly. Okay, so what is a stable graph? A stable graph is what stable graphs do for a living is enumerate possible degenerations of the worldsheet surface. The word stable just means that each component is itself a Riemann surface that supports a hyperbolic metric, if you wish. So if it's genus 0, then there are at least three punctures or boundaries. If it's genus 1, then there's at least one, and for higher genus, there's no restriction. So each stable graph you should think of as a set of vertices, which is itself, each vertex, it is itself a Riemann surface. And those vertices are connected along the generated points, or these nodal points. So here's an example where I took a 4-hole sphere and combined it by 2 pairs of pants joined at a nodal point. There's also, of course, the one with no degenerations itself. And the word color here just means that to each vertex, to each component, I associate an integer m, which is bigger than or equal to 1. Now, given a stable graph, which again is made up of a number of vertices or components joined along nodal points, there's a vertex factor for each vertex, and you integrate over the momenta associated with each of the nodal points over a complete set of states in the worldsheet theory. And then finally, for each vertex, there's this vertex factor is proportional to this corresponding quantum volume of the Virasoro minimal string. If you process all of this, it reproduces, for example, the A04 that I wrote down earlier. So this sum over colors of these stable graphs is precisely the sum over branch points in the dual matrix integral. And we see that this, the Virasoro minimal string quantum volume plays the role of a string vertex in the sense of closed string field theory. Okay, so that's it for the stable graphs. Just to make it concrete, let's revisit this formula we had earlier for the sphere 4-point amplitude. There are 2 distinct kinds of stable graph. There's this one without degenerations, and there's the one where you degenerate it into 2 pairs of pants, plus 2 permutations based on how you pair the external legs. There's an external leg factor for each of the boundaries. There's a vertex factor proportional to the Virasoro minimal string quantum volume. And then we integrate over the momentum associated with the nodal points. And this exactly reproduces the kind of horrible looking formula that I wrote down a number of slides ago now. Okay. Now we can take topological recursion for the matrix integral and translate it into a recursion relation for the string amplitudes themselves. And this translates into a recursion relation for the string amplitudes that is in a very precise sense a deformation of Mirzakhani's recursion relation for the Weil-Petersen volumes. In fact, I wrote down in the talk here last year an almost identical slide with essentially one difference that I'll highlight in a second. So the way this topological recursion works is you sum over the topologically distinct ways of embedding a pair of pants with a distinguished external leg into your world sheet surface. So here I've picked this leg P1 in this torus 2-point amplitude. So there's sort of three distinct ways of embedding it. There are these sort of non-separating embeddings where you reduce the genus and add a leg to the rest of it. There are these separating embeddings, which roughly divide the world sheet into two distinct components. And there are these embeddings where the pair of pants shares a cuff with another external leg, where you reduce the number of boundaries by one. Now, associated with each graph, there's also a factor of the sphere 3-point amplitude associated with this privileged pair of pants. And that really is the only difference between this and the formula I wrote down last year in the talk here. The reason being that in the Virasoro minimal string, the V03, the quantum volume associated with the 3-punctured sphere, is just one. So this was, whereas for us, it's this funny elliptic function of the 3 momenta. Even the recursion kernel that enters this topological recursion was the exact same as that in the Virasoro minimal string. So it's really structurally not just similar, but identical to the recursion relations for these quantum volumes in the model I talked about last year. So this, all these ingredients conspire to solve the theory at the level of string perturbation theory. Okay, so now we're in the last chunk of the talk, and I'll tell you about the connections that I think quite exciting connections to low-dimensional de Sitter quantum gravity. Are there any questions before I move on from the world sheet, the matrix model? Okay, good. Okay, so stepping back a little bit, an obvious observation that we as theorists have to reckon with at some point is that our universe appears to be undergoing some form of accelerated expansion. And it would behoove us, I think, to formulate holographic scenarios that accommodate such a situation to the extent possible. But of course, there are theoretical obstacles to doing this. Otherwise, we would have been doing it already. And I think one of the important theoretical questions in this arena is just a very basic one. What are the well-defined or gauge invariant observables that we should even be talking about? In ADS CFT, of course, it's the correlation functions of the boundary CFT. But it's less clear in situations in cosmological scenarios what the proper observables should even be. And another question we could imagine asking is, where does the holographic screen even live? A more specific question would be, what are the microscopic degrees of freedom that account for the entropy that's associated with the cosmological horizon of an observer, which has been known since work of Gibbons and Hawking to encode an entropy loosely analogous to that of a black hole horizon. And of course, our approach, as always, will be to develop controllable models where a microscopic formulation might be possible. So the setup for this discussion is the following. We'll discuss the canonical quantization of what I think is one of the simplest possible models of an expanding spacetime, which is 3-dimensional de Sitter Einstein gravity. And we'll consider the canonical quantization of the theory on some initial value surface, sigma. The surface may be punctured, which means these extend to Wilson lines in the bulk, which we think of as world lines of massive particles. So we can imagine endowing this theory with the world line action of some massive particles. But I'm not doing perturbative quantum field theory in de Sitter space. This is a simplified setup.
Sorry, what are the punctures?
We think of the punctures as on the initial value surface is being associated with the world line of some massive particle in the
What are
bulk.
they described as in the formula, the variables that you've written there?
There would be some plus world line action of the massive particle. We think of them as being so heavy that they back react and source like a conical defect in the space-time. In some sense, we think of them as being part of the background that you're considering to begin with, rather than perturbative quantum fields living in this de Sitter space-time. It's precisely analogous to the situation with conical defects like ADS, CFT. Okay, so to speak of the canonical quantization, we have to start with the classical phase space. Now, this is parametrized by the two-dimensional metric on the initial value surface together with the extrinsic curvature. And we can pick a polarization so that we think of the wave function associated with this canonical quantization as being a function only of, say, the metric on that initial value surface. Now, there are constraints in gravity. So really, we should think of this wave function as being a function not just of the metric on this initial value surface, but the metric mod diffeomorphisms and Weyl transformations. So the reason for that is because of the momentum constraint, let's say the ADM formulation of 2 + 1 dimensional gravity, which generates diffeomorphisms along the initial value surface, and the Hamiltonian constraint, or the Wheeler-DeWitt equation, which generates time translations, which essentially amount to Weyl transformations because we're in an expanding space-time. And what this means is that we should think of the wave function as really depending on the moduli space of the conformal class of metrics on this initial value surface. And well, at least in the ADS case, but the de Sitter case we show is closely analogous, processing these constraints leads you in a precise way to the Virasoro ward identities associated with the conformal blocks of this initial value surface. So the upshot of this canonical quantization is that the Hilbert space is spanned by Virasoro conformal blocks living on this initial value surface.
Sorry, if you remove the punctures, what is the dimension of this Hilbert space?
3G minus 3.
So
If you add the punctures, it's 3G minus 3 plus n.
So you do not assign a one-dimensional Hilbert space to the closed universe?
No.
How are
Yeah.
we supposed to interpret that?
I think it has to do with, in this discussion, I'm gauging the mapping class group after quantization. So the quantization sort of doesn't see the fact that we gauge large diffeomorphisms.
Okay.
We'll see the way in which this Hilbert space enters. We'll eventually end up thinking of this surface as a late time like future infinity scribe plus in some cosmological space-time.
But if you were to, just to come back to the point, if you were to gauge the mapping class group, you would get a one-dimensional Hilbert space?
It's unclear. It's unclear. Many aspects of the Hilbert space of this theory are unclear. It may become more clear the sense in which things are unclear as I go. Okay, so at least in this discussion where we quantize and then gauge large diffeomorphisms, a complete basis of wave functions transform like Virasoro conformal blocks with this central charge. So this imaginary part is basically the analytic continuation of the usual Brown-Hainaut relation in ADS3, just with an I sitting in front. And this 13 is a one-loop correction that's been known essentially since work of Giambi, Maloney, and Yin in 2008. Okay, so that's the central charge, and the external particles that parameterize the punctures on this initial value surface are associated with conformal dimensions that live in this SL2C principal series. And these are related to the masses of the particles in the bulk, essentially by the DSCFT dictionary. This is also essentially an analytic continuation of the ADS relation. Now, this Hilbert space is equipped with an inner product. So, of course, to talk about a Hilbert space, I need to tell you both the vector space and the inner product. And that inner product suppose you're given two states, chi and psi, associated with some initial value surface, a genus G surface with n punctures. Then up to normalization, the inner product is defined by integrating the wave functions or the associated conformal blocks over the moduli space of Riemann surfaces. And I've done something a little slippery here, which is that, I'm saying that in gravity we gauge large diffeomorphisms, so this integral runs over the moduli space. And so we assume that the wave functions are crossing symmetric combinations of conformal blocks, otherwise known as CFT correlation functions. If I was instead to work with the Hilbert space where we gauge after quantization, then this integral would run over the Teichmüller space, the universal cover of the moduli space. And these wave functions would not need to be crossing symmetric. But for the application in this paper, or in this talk, we can assume that the wave functions are crossing symmetric. And the main conceptual point I want to make here is that this inner product precisely takes the form of a string world sheet moduli space integral of the sort that I talked about in the first part of the talk. Okay, so now suppose we're in some situation where the future infinity, the light time slice, is some genus G surface with n punctures. The question we should be asking ourselves in this 3D gravity setup is, what is the wave function of the universe that defines the state at Scri plus? I say that it defines some state because there's some, the path integral will be some linear combination of conformal blocks associated with this surface. Now, one thing I want to emphasize here that may be different from other discussions is that there's a famous proposal in the literature, the no boundary proposal due to Hartle and Hawking, but applied in this context where the Cauchy slice is a hyperbolic surface in the 2D sense. I want to say that this proposal does not seem very natural. So let's consider the case without punctures just for simplicity. Then the sum the way you would define this state would be to sum over handle bodies associated with this surface. I say handle bodies because in the no boundary prescription, we smoothly cap off in a Euclidean way in the bulk. And a handle body is simply a smooth filling in of the boundary Riemann surface. So we would sum over different ways of filling in this Riemann surface into a handle body. And potentially there would be corrections from higher topologies, more complicated topologies than just handle bodies. And this sum does not seem very well behaved. So the way I've described it here, it sounds essentially exactly like the analytic continuation of the partition function, of the computation of some partition function in ADS3, but now in minus signature, so as to support a positive curvature metric. So the sum involves some complex geometries and this funny triple minus signature. Moreover, equipped with this inner product I told you about last slide or 2 slides ago, each term in this sum gives a non-normalizable contribution because there are divergences near the boundary of moduli space of these handle body partition functions. Finally, and perhaps conceptually most importantly, this sum over topologies is completely uncontrolled. Now in ADS CFT, this sum is controlled because each term in the sum over topologies goes like e to the minus c times the renormalized volume of the topology. However, here c is 13 plus I times a big number. And so what that means is that the higher and higher topologies give more and more rapidly oscillating contributions to this Hartle-Hawking state.
Is it a discrete sum? Like, is it a sum or is there?
I think it is a discrete sum for the same sense that it's a discrete sum in ADS CFT. Hyperbolic manifolds are.
No, but once you say complex geometries, I don't know what you're.
Yeah, I guess you're saying that I'm assuming that they're on shell and the opposite signature, and maybe that need not be the case. Yeah.
And then the question that you're asking here, I mean, you have the state and you have the polarization. So in a sense, don't you have the answer? Like
I don't have a specific state yet. I'll tell you how to.
But if you give me a state in a conformal block, you have the polar, right?
A crossing symmetric combination of conformal blocks with the right central charge and conformal weights would be a candidate state.
But it's always the question like, give me a path integral interpretation of the state? Is that-
Yeah, I mean, I also think there probably aren't that many candidate states with this value of the central charge. I mean, also that another caveat would be that state may not be normalizable in the Hilbert space. Maybe that's not an essential obstruction, but
So why do you not like extremely rapidly oscillating as opposed to exponentially damped? In some high epsilon sense.
maybe it's fine, but conceptually I don't know, the nature of this sum seems completely uncontrolled.
And the other question was, what's the role for global de Sitter space here? Because
Good question. We'll come to that at the end of the talk, but yeah, it's not clear. This is maybe as close as an answer to that as I'll get. So the strategy instead will be to consider an explicit solution of the equations of motion that has all the properties we're looking for. So let's consider this following model for an expanding universe in DS3 with a late time slice given by this genus G Riemann surface. So this expanding space-time has the following extremely simple on-shell metric. In a loose sense, you can think of this as a sort of de Sitter version of the Malta-Saint-Amau's two-boundary Euclidean wormhole in ADS. So here, d sigma squared is the constant negative curvature metric on the light time slice. And one thing you'll notice about this topology is that it has a Milne type Big Bang singularity at t equals 0. This is not a genuine curvature singularity because the curvature is constant, positive everywhere. But nevertheless, it has this Big Bang type singularity. And in fact, you can show that there are no non-singular on-shell topologies that admit these hyperbolic Cauchy slices. So this singularity, unless you do some funny contour rotation in time, seem to be a fact of life. Okay, so this seems like a nice candidate for defining a wave function of the universe. And indeed, we can use recently developed TQFT technology for 3D gravity to compute the gravitational path integral on this expanding cosmology. And our strategy will be to compute it by analytic continuation of a related two-boundary wormhole in Virasoro TQFT, the ADS3 version. And in fact, the metric on this expanding space-time and that on the Euclidean wormhole are related by a different contour for time.
It doesn't pinch in the middle? I don't understand this geometry. When this top thing suggests that the wormhole should pinch completely in the middle? Or is
It does, yeah, maybe this is the order I presented things in is confusing. Here, if I just do this change of time contour, the metric literally becomes that of.
Oh, it reaches some minimum size. I see.
Yeah, exactly. At rho equals 0, yeah. So the way we computed the path integral on this thing was to model the singularity by a sort of topological boundary condition for 2 copies of Virasoro TQFT, which are what define ADS3 gravity, at least on a topology by topology basis. And then we can use a trick familiar in the TQFT literature, known as the unfolding trick, I think, where we take this two-boundary, or this topology in 2 copies of the TQFT with this topological boundary condition, and unfold it into a configuration with 2 dynamical boundaries in 1 copy of the TQFT.
Is there something distinguished about that boundary condition? There are probably many boundary conditions.
Yeah, not that we know. Not that we know. We don't understand the space of topological boundary conditions for 2 copies of VTQFT well at all. But we wrote down a candidate for what this should be. Roughly, it freezes the gauge fields in the Chern-Simons formulation. Okay, anyway, now this configuration on the right-hand side, we know how to deal with using these recently discussed TQFT techniques. And what do you know? If you compute the path integral on this Euclidean wormhole topology in a single copy of the TQFT, what you get is the correlation function of Liouville CFT on this surface sigma GN. And then to continue back to DS3, we simply continue the central charge and the conformal weights. So this is some convoluted procedure to convince you that a natural candidate for the cosmological wave function is this Liouville correlator, which appeared as an ingredient in the worldsheet formulation of the theory. So we take our cosmological wave function to be defined by this correlation function, which is some privileged state in this Hilbert space where we gauge the mapping class group and then quantize because the wave function is crossing symmetric. Now, this wave function, in contrast to the Hartle-Hawking state that I discussed a few slides ago, has some desirable properties. So for one thing, it behaves like a CFT correlation function if you factorize the late time surface.
But why should that happen for a wave function? Or is that just some DSCFT intuition?
It's some DSCFT intuition, yeah. Now, it's crossing symmetric on its own, which if you think about it is kind of remarkable because we started with a single topology in the bulk and the wave function that we derived from that was crossing symmetric on its own. So what that means is that in principle, there doesn't seem to be a need for any further sum over topologies in the bulk. And in fact, we weren't able to convince ourselves of the existence of any other topologies in the bulk. So it could be that they exist, but we're not aware of any other candidates that one could consider in contrast to this Liouville state. And finally, it's in fact a normalizable state in this Hilbert space. So the norm in this Hilbert space is defined by integrating mod psi squared over the moduli space of Riemann surfaces. And of course, that is just the definition of our string amplitudes that I was discussing in the beginning of the talk. Yeah.
I'm sorry, I actually lost the track of P. This is coming from the original where you wrote the weight in terms of the discernments, or
Yes. The P here, so this bold P means it's some collective variable, P1 through Pn. And these are momenta fixed by the masses in the bulk through the DSCFT relation that I wrote here.
I see.
So in particular, P conformal weights in this principal series mean masses bigger than 1 over L.
So when you write down explicit expressions here, the parameters that appear are basically the mass.
Yeah, the masses of the particles and the ratio of the de Sitter length to Newton's constant.
I
It's
see.
the central charge. Yeah. And that's really all we know, right? Because in principle, all we have access to is this late time slice. Okay, so I'm running out of time, so I'll try to wrap up in a couple minutes. Now, just to take a step back, the gauge invariant observables in this theory a priori. So one often talks about cosmological correlators of late time fields or particles on some de Sitter background. But for those observables to be well defined, really what you should be doing is integrating over metrics on the late time slice because gravity is still fluctuating at future infinity. Now, in our de Sitter 3 discussion, we've been discussing very massive particles that back react on the geometry. And so we think of them rather than entering the cosmological correlator in this sense, they're so heavy that we think of them as modifying the wave function itself. And so that's why our string amplitudes, or integrated cosmological correlators, take the form of an integral mod psi squared. And so what this establishes is a kind of funny and I think quite novel duality between these integrated cosmological correlators, which are equivalent to these string amplitudes of the complex Liouville string, which remember in turn are themselves dual to the resolvents of this dual two matrix models. There's some duality between these integrated cosmological correlators on the one hand and resolvents of a two matrix model on the other. Now finally, it's widely believed that the sphere partition function of de Sitter quantum gravity encodes some sort of entropy associated with the cosmological horizon. And so far I've been discussing these integrated cosmological correlators of these massive particles on expanding space-times and establish some funny duality with a two matrix model. But I think it's fair to ask, those considerations seem more global. This de Sitter entropy is something more associated with the static patch. You might ask, to what extent does this duality know about the de Sitter entropy? So now we return to Emily's question from earlier, where we try to count the number of degrees of freedom enumerated by this density of eigenvalues of one of the matrices before we hit the first zero of the density of states. So let's call this n. I probably should have put some subscript or something to distinguish it from n of the matrix model, but we'll define it by integrating this leading density of eigenvalues over the region where it's positive, initially positive. And what we get is some explicit function of b. Now there's some trickery here, because you see e to the s naught enters, and I need to fix that in terms of b, because remember, 3D gravity does not have a genus counting parameter intrinsically. It has g nu. And so consistency of this 3D TQFT will relate this e to the s naught parameter and 1 over b, which encodes g nu of the 3D pool. I won't tell you how we did that, but trust me that it proceeds in this way, and you get this simple answer for the number of degrees of freedom in this window. Now, if you take the log, if you square this and take the log, it leads to a microcanonical, maybe it's more like a Shannon entropy, that reproduces the sphere partition function in the semi-classical expansion. So in particular, the Gibbons-Hawking term comes out correctly, but also the one loop logarithmic correction comes out with the precise correct prefactor. And if you fix this carefully enough, you can even convince yourself that the order g Newton to the 0 component comes out correctly, including a phase that's recently been emphasized in the literature. Okay, so let's take stock of what we've seen. So just to emphasize, the duality is between resolvents of the matrix model and integrated cosmological correlators, integrated over the metric at future infinity, and not the cosmological wave function, as in the older picture of DSCFT. That's partly because the cosmological wave function is not, should not be thought of as a gauge invariant observable. Now, of course, since we anyway integrate over metrics at future infinity, why not sum over topologies? Now that sum is asymptotic and will require some non-perturbative corrections, which are related to these ZZ instantons I discussed earlier. I think it's interesting to ask, what is their interpretation in DS3? I mentioned this earlier, but the string theory and the matrix model both have this genus counting parameter e to the minus s naught, where b is an independent parameter of the theory. Whereas in 3D gravity, there's no intrinsic genus counting parameter. You just have g nu. And the message of this bullet point is just that they turn out to be related by consistency of the 3D TQFT. If you're interested in how this works, I'd be happy to discuss after. Okay, so finally, just to emphasize the difference with ADS-CFT, it seems to work quite different. You know, in ADS-3 gravity, for example, it's been understood that the path integral computes some universal contribution to some delicate ensemble of statistical moments of the boundary CFT data. Whereas in 3D de Sitter, the observables are integrated cosmological correlators, which are in turn related not to a CFT, but to a matrix model. And I think the difference between these two paradigms can be traced back to the difference in the nature of the good observables. They seem to be fundamentally different for quantum gravity with positive and negative cosmological constants. Okay, so that's more or less the talk for today. I told you about the worldsheet description. The main observables are these closed string amplitudes, which we determine through a sort of analytic bootstrap. We realize these as resolvents of a double-scaled 2-matrix integral, and finally as integrated cosmological correlators and 3D de Sitter quantum gravity. There are some other interesting aspects of this story. Feel free to ask if you're interested afterwards. And with that, I'll wrap up. I'll leave some future directions on the screen. Thanks for your time.
Questions for Scott?
I'm confused by a basic thing. So why the wave function for in the de Sitter gravity theory suddenly equal to the correlation functions in the Liouville theory?
I mean, a priori, it maybe
Was that a
sounds
guess?
surprising. Well, I mean, it wasn't just a guess. There are a couple of routes that led us to this proposal. One is the computation of the gravitational path integral in this inflating space-time, which is the only well-behaved, let's say, topology, like Lorentzian topology we could think of that would solve the equations of motion. You can also, I think, land on this Liouville correlator by just demanding some simple constraints that you want the wave function of the universe to satisfy. Primary among them being normalizability. Yeah, I mean, you might ask how unitarity of the 3D bulk selects this particular state, and we don't really understand unitarity of the 3D bulk very well, so I'm not sure. But anyway, this was more than a guess. It was computed based on the computation of the gravitational path integral in this space-time. And you could also sort of bootstrap it more or less uniquely by demanding these physically desirable characteristics, let's say.
Does it also happen in surface with boundary?
Yeah, that is a good question. Yeah, if the late time slice itself has some boundary, yeah. We have not thought about that. It's a question I would often get when discussing the TQFT for 3D gravity. What about the Hilbert space if you cut along some surface with boundaries? And it hasn't been formulated. So it would be nice to understand.
Sorry, so maybe you say this that the sphere partition function, isn't there a factor of I?
There's a factor of I, there is, that's right,
yes,
hiding in the G Newton to the 0.
Can you see that in the matrix model?
Well, notice that B squared enters here. B squared is imaginary.
So, okay, so that n is not a real number.
Yeah, in some sense, yeah. And it involves this funny pairing between e to the s naught and 1 over b, which implicitly gives some phase to e to the s naught if you take it too literally. But yes, there is some factor of, I think it's 5 pi over 2 argument of this de Sitter entropy. Yeah, that we haven't gotten rid of. What you would like, I think what you would like to have that I haven't discussed here would be to compute this sphere partition function directly in the bulk using something like a de Sitter version of Virasoro TQFT. That I did not present. But there's reason to believe that you land on a very structurally similar answer to what I wrote here.
You mentioned the genus expansion in this case is asymptotic.
Yeah.
It means that it's not resolvable as in say c equals 1.
Let me see, there are alternating signs in the genus expansion, which is often a sign of Borel resummability. I don't think we have any sign that it is Borel. You're asking about the ambiguity of the non-perturbative corrections, I guess?
Yeah, I mean, or I just wanted to compare it with say c equals 1.
Yeah, well, there in C equals 1, they are unambiguous, at least in the
Right.
in particular sectors. Here, I think in principle, there is an ambiguity having to do with how you deform the eigenvalue contour on the matrix model side. But I think there's similarly an eigenvalue or an ambiguity on the string theory side. And the idea is that those ambiguities align.
I see.
And that if you fix it on one side, you can fix it on the other. But yeah, I guess just one structural comment I'll make. I'm not exactly sure about Borel resummability, but the genus expansion, because of the fact that this string coupling is pure imaginary, it does alternate in sign, which is often a hallmark of Borel resummability. But yeah, I don't know that we know enough to say whether it's resummable or not.
Any other questions?
Is there any knowledge for this large genus asymptotics for the quantum volume?
Yeah, that was one thing. So for the quantum volumes, we worked it out in the Virasoro minimal string paper. Essentially using standard resurgence techniques, and there's an almost identical formula for the AGNs as well.
Does it coincide with the one with the usual volume? Or
Yeah, with the Ve Peterson volume, you mean? Yeah, that's right. There's some decorate some formulas with B's, but yeah, it's structurally very similar. 2G factorial growth.
Another perhaps a big question.
Mhm.
It seems like there's always these principal series representation.
Yeah,
Do you think you can use harmonic analysis to write down some sort of conversion?
harmonic analysis on SL2C.
Yeah.
Yeah, I mean, that's kind of what we're missing here is something like the Euclidean inversion formula
Yeah.
for the principal series of like higher dimensional CFTs. Yeah, we need something like that. So a complete basis of I sort of swept this under the rug, but I was talking about how conformal blocks are some basis for this Hilbert space, but then I swiftly moved on to talking about the case where we gauge the mapping class group and only talk about CFT correlation functions. Yeah, I think in order to formulate this complex Virasoro TQFT, one will need a better handle on these on this ungauged Hilbert space, for which you need a complete basis that's like orthogonal with respect to this inner product, something like a Virasoro version of conformal partial waves in higher dimensions. And that we don't have a convincing proposal for.
Let's thank the speaker again.